Hello everyone. In this video, we're gonna talk about the concept in the atomic structure, which is called isotopes. Okay, so we already briefly introduced you there are three particles in any atoms. There are protons, neutrons, and electrons. Okay, and by definition, number of protons is defined to be the atomic number, and electrons usually, okay, especially would be the same as number of protons, which is also the atomic number, and the neutrons and the number of protons add up to the atomic weight. Okay, so in other words, when you read the periodic table, the atomic weight minus the atomic number, that should give you the number of neutrons. Okay, so all of the atoms basically are composed by protons, neutrons, electrons, three things. Here we want to briefly explain why when we have three choices, okay, number of protons, number of neutrons, number of electrons, we only use number of protons as the identity of the elements or atoms, okay, because essentially the difference between the elements or atoms, they're just because they have different number of things, different number of these subatomic particles. But why not using number of neutrons, number of electrons? Well, the electron is simple, okay. You can in chemistry, okay, generally we're talking about elements or atoms losing electrons or gaining electrons. So electrons are flying out there, okay. So they are actually the material to be used doing chemistry, doing interactions with other atoms. So you can fairly easily compare to neutrons and protons nucleus, relatively easier to lose them or gain them, okay, which we're gonna touch more, get more detail about that. So number of electrons may change over the time, in different processes, okay. What about neutrons? Okay, neutrons are located in the nucleus as well, along with the proton making up the nucleus. It has the same mass as the proton, but it doesn't have any charge. Okay, so can you have different neutrons as the same element? The answer to that question is yes. So that introduces you the concept of isotope. Okay, so basically by definition, when you are kind of elements, okay, that means you have the same number of protons, okay, because we use number of protons to identify the element, okay, same atomic number. But you could have a different number of neutrons in the nucleus. And of course, because atomic mass is the sum of the neutron and the proton, so when you have a different number of neutrons, your mass number will be different as well. Okay, as a matter of fact, there's no exception. All of the elements, they have isotopes. Here's a quick example showing you three different isotopes of hydrogen, okay, which is number one element. Number one element, here you can see we're using a little smaller circle representing the nucleus and the larger circle representing the the orbit electron traveling on. And you can see this little plus symbol representing the number of protons with positive charge. We can also use a little circle inside the smaller circle representing the neutral neutrons. Okay, so most of the hydrogens, okay, are having one proton and one electron and no neutron. So in other words, the atomic weight of this hydrogen is going to be just one because of one proton. You can see all three hydrogens, they all have the one proton. Okay, the difference is the second one has one neutron, and the last one has two neutrons, which basically will make up 2 AMU atomic weight and a 3 AMU atomic weight. Okay, so there are three isotopes exist in the hydrogen element, and that's also the reason why we don't want to use the number of neutrons to be the identity of the elements. Simply because you can possibly have different number of neutrons. I'm sorry, even though you are the same element with the same number of protons and neutrons. The main difference is the atomic weight. Now we want to take a look at another example, okay, of the isotopes. So, like I said, there's no exception. All of these elements on the periodic table, they have isotopes. Okay, for instance, when you look at carbon, which is number 6, number 6 is the atomic number. Okay, so when you look at carbon, Oh, sorry. When you look at the carbon, number of proton, which is the same as atomic number, and that's 6. Okay. Now, according to the periodic table here, usually you will find a mass number 12.011. Okay, and it can be easily round down to 12. And then you would have a number of electron. We use a E with a negative symbol on top representing electron. Okay, will be the same as number of proton, which will also be 6, and number of neutron will be the mass number minus the number of proton, so it will be 12 minus 6 equals 6. So most of the time you're looking at a carbon with 6 proton, 6 electrons, and 6 neutrons. But there could be an isotope of carbon. Let's say this isotope, of course, it has 6 protons and 6 electrons, but it has, instead of 6 neutrons, you may have 7 neutrons. Okay, so when you have 7 neutrons, the mass number will not be 12 anymore. Mass equals to neutrons is 7, protons 6, and the mass number is going to be 13. So that's the main difference between the isotope of carbon with another different isotope of carbon. Okay, it has different mass numbers. So how about this mass number? This mass number obviously is closer to 12, whereas this mass number is 13. Which one should we take? So we want to explain a little bit more. Okay, so as you can see, not just carbon, all of these elements, okay, they all have a mass number which is not exactly integer number or whole number. Okay, presumably if you're just adding up number of protons and number of neutrons, both are in which both are whole number, your mass number should be a whole number, right? But it turns out none of these are. Okay, if you take a closer look at all of the mass numbers, none of these are whole numbers. The reason is that these are not just the mass number for any atom. These are the mass numbers of the average of all different isotopes of the same element. So for instance, if you have a carbon with 13 mass number, and you have another carbon with 12, the average of these two will be 12.5. That's where these decimal points resulted from. But of course, this is just a lousy example. Okay, the actual average, you have to count in all of the isotopes, as well as the natural abundance of those isotopes, like which you may always have one isotope that's pretty much dominating the rest of the isotopes. Okay. Now, which number do we take though? Well, it depends on the question, I think. Okay. So if you're given a specific number of neutrons, that means in the test or in the homework, okay, that means I want you to deal with this specific isotope. For example, if I give you carbon with 7 neutrons, then I will be asking you for a mass number that's 13 instead of 12. Okay, so just be aware that when you're looking at a specific atom, you need to be specific about number of neutrons and mass numbers as well. Or if you're not given a specific number of neutrons or mass number, then you can take the average mass number, which is usually close to a whole number. Okay, it can be easily round to a whole number, and so you can calculate the number of neutrons from that. Okay, all right. So this is the isotope.